So if you remember from the previous session, we were at the end of this. So we were making this computational graph. So in this way, if we had an expression, let me just remind you a bit what we're trying to do. Okay, we'll take an example. Suppose I have written over here that this example is there. So let me just copy and paste the example, and then we'll make computational graph for that. Just give me a second. So let's suppose if you see the expression over here at this expression, now we can use the same expression. Say we have this A, B, and C are the parameters, and we can make a little bit complex with this. So let's consider this A, B, and C. Let me see also, so that I don't deviate much from the code. I would like to copy the values from here. So let's suppose we have A, we have B, we have C, and we have, let's suppose, E. Okay, I don't know, this is some new input which I inserted. So if you see this D is equal to A multiplied by B. Okay, and this is the value. And then we have F is equal to D plus C. The final expression that if you see is this. This is the final expression, A multiplied by B plus C and whole multiplied by E. So if I show you this, so this is the expression. So now if you want to see the computation graph of it, the only thing you need to give it is the root. So if I see draw dot, this is what we have, the code that we wrote in the previous session. So you will have to only give the last node, the root node. The root node over here is G, I suppose. So if you give this G, okay, so if you print this, so you will see the computation graph. This is like this. So you have A multiplied by B, and then you have plus the C, and then you have whole multiplied by this function, and then you're getting this output. Okay, I hope this is clear for everyone. This is what we were doing. And now in order to first do the back propagation, I told you we'll do back propagation manually. So we'll do it step by step. So each of these nodes, if you can clearly see over here, so it has a label, that's what we wanted to print, and then it has data, the data that is inside the node. And then we have the gradient corresponding to that node. And considering that each of this is having the gradient, and by that I mean, so if we have the loss function at L, so let's suppose this is last loss function. If we have this, okay, so consider this one over here. I could have given these nodes also some names. Let's suppose this is the loss function, and this loss function has some value. Okay, that data is the value, and this is computed by all of the nodes that came previously. And if I define gradient for something, that means that thing will be considered for the loss computation. So that will impact loss somehow. So if I do not consider gradient for a particular thing, so consider that I am not taking that particular node in the picture of the loss. So I'm saying this is not affecting the loss. Okay, usually let's suppose all of these right now are affecting the loss, but when we're making the real network, in that input will not be affecting the loss. Why? Because input will be fixed. I don't have to assign gradient to inputs, but in this case I am assigning gradient to all these nodes, because I want all these nodes to somehow contribute, and I should be able to nudge these values and see what's the impact on the loss function. Okay, with this being said, and before doing the manual back propagation, I'll first tell you the methods, because we have seen some methods of computing the gradient. So one among them you saw was the numerical method, in which we do the definition, and by the help of that we compute the gradients. We compute the derivatives, and a bunch of derivatives is called the gradient. And then the second thing is which is called symbolic differentiation. Okay, you can also use symbolic differentiation, but it's, again, we're not using it in the computers, but you can use it on the pen and paper. So how does that look like? Let me show you. So if you now see this, so we can have symbolic differentiation. So what is symbolic differentiation? So whatever you studied in the class of calculus that was covered previously, so what basically that was symbolic differentiation, in which you have rules. So you'll have some product chain rule, you'll have some rule, okay, you'll have product rule, you have, when you have composite functions, you'll use chain rule. So all these rules were used in that. So you do the differentiation symbolically. If you have let's suppose a function f of theta, okay, and then this function is equal to, let's suppose pi I goes from 1 to suppose some k, you have theta I, and you are asked to find the derivative with respect to particular theta of this function. So what you will do is you will use the product rule in this case. Okay, so let's suppose if this is with this, so you'll say the answer is I is equal to let's suppose we'll say j is equal to 1 to k, and j is not equal to I, something of this sort, and this is theta of j. So you will consider this like that. And what you have done over here is, because you consider all other terms as constant, and only this ith term theta I was taken derivative with respect to this, so that this is what it came up with. So again, if you are given an expression, you can use some rule, product rule, or chain rule, and you will do the difference symbolically, and we will not usually use this again because this is costly. So if you see, for each of this you will take some n-2 operations, and you will have to do it for say n nodes. So what will happen is, so you'll take n into n minus, so this goes to quadratic, so we won't use this. So instead of this, the third method that we'll say, the first method we saw is the numerical method of differentiation. You'll use the definition of differentiation, or definition of taking the instantaneous rate of change, and then you'll use that, and based on that you'll compute the derivative. The second rule is the rule that we have been seeing in calculus. You'll use rules of calculus in order to get to that. Again, I told you there is again a problem. It's not computationally efficient. The third thing that we'll do, that is the concern of today's lecture, is called as automatic differentiation. So what is this automatic differentiation now? Okay. So now in this we compute the computational graph, and then we try to see in our computing systems, in our hardware that we have, can we somehow implement it in such a way so that many of the things are done automatically. So there is a way to automate this. That's why it's called automatic differentiation. Okay, you just apply this from a particular node and it should compute the things on its own. And in that, one important concept is computational graph, that I have spoken at length in previous lectures as well. So computational graphs are made first, and whatever we made so far in our code, so that's actually a computational graph. If you see, we made that graph sort of thing. We have node A, node B, and then it multiplies. We make some other node based on that, and we had gradients values as to that. So that's the computational graph in that. Okay, so taking a standard example from some slides from Carnegie Mellon University. So I'll make computational graph. So you have a graph like this. Suppose you have x1 and x2, and then consider this as node v1, and I'll first write the expression. The expression goes like this: y is equal f of x1 comma x2. It takes two inputs, and this expression is equal to log of x1 plus x1 multiplied by x2 minus sine of x2. So this is the expression, and we want to draw a computational graph for this expression. Okay, so let me draw it with some other color so that it's visible. So this is the expression. So now how to do this? This is x1, x2, and you have v1, and this is v2. Basically, we start with v1 and v2, we directly give them the values x1 and x2, and then we apply log on this. So once we apply log on this, so let's suppose we'll get v3. Okay, so this is the first function. So then we have to do x1 multiplied by x2. So we'll multiply this. Okay, so we'll multiply this x1 multiplied by x2. Okay, you're multiplying this and you are getting some node. Let me make these nodes better. Okay, so you are getting this node. Let's call this as v4. Okay, after this, once you have this term, now you have this term, and you add them up. So you have to add these things. You will do this, and this will do addition. So here you did multiplication, in this you did addition. So now you will get one more node. Let's call that v6. Okay, and after that, what we are doing is you are then saying minus of sine x. So you'll apply sine on this x2. So apply sine on this. So you'll get some v5. You are applying sine on this. Okay, and then you are subtracting these two things. So you are subtracting these two things, you are getting v7, and you are subtracting this over here. So this over here, what I made is a computational graph. So if I write the same expression in whatever we did, whatever we have written the code for, so you will get a graph of this sort. Okay, something like this. So now the first thing is, if you have to evaluate it, you know, we have to do the forward pass. So how to do forward pass? So if I take the values, so the values that are given here is x1 is 2, x1, the value of x1 is equal to 2, and the value of x2 is equal to 5. Okay, these are the values. So the first thing that we have to do is we'll do the forward evaluation trace. Okay, so we are doing forward pass. This is what we'll be doing. So how can we do that? We'll start with these notations only. So this is just syntactic sugar. This is nothing else. It will be pretty easy. I'll just write it for the sake of completion. So we have v1 is equal to x1. So v1 is equal to x1. That is equal to 0.5. Okay. And similarly, we have v2 is equal to x2, that is equal to 5. So if you see it, at 2, you should not write 0.5, this is 2. So if you see, this is x1, this is x2, and I'm just filling these values, v1, v2, v3, v4, v5, v6, I'm just filling them out. Okay, so v1 is equal to x1, that is 2, v2 is equal to x2, that is 5. And then if I see v3, so how did we get v3? So v3 was, we applied log on this v1. So this is equal to, roughly equal to 0.693. And then we'll get v4. So how is v4? How did we get v4? x1, x2, that is v1 multiplied by v2. So this is equal to 10. 2 multiplied by 5 is 10. And then we have v5. How did we get v5? So v5 was sine of this. So if you see v5 over here, so this was sine of x2. So sine of v2. and the sine of v2, once we apply that, so this is roughly equal to minus 0.9589. And then similarly we have v6, so this v6 was equal to v3 plus v4. Okay, these two terms, if you see from this expression, log term plus this x1 x2. So if you evaluate these two things now, so you have values of v3 with you have values of v4, you have to come with this. I think this should be 10.693, roughly equal to this. And then v7 is a subtraction, so you'll subtract this, so this is equal to 11.652. This is how we perform the forward pass. Okay, pretty easy. And now in this, if you see, each node here stores an intermediate information. So now we are not just taking this, we are taking each of this node. So if you take the v3, so v3 was not originally in this expression, but we made it somehow, so this is called v3. Okay, and if you see, let's suppose this is a separate node and these two together are a separate node. Okay, so each thing is an intermediate computation, so each node holds some intermediate computation. So I want you to know these things. So the first method of auto graders or auto differentiation or automatic differentiation is called as forward mode of auto differentiation. So this is called as forward mode automatic differentiation. Okay, so we will see how to apply this. Again, it will use the same rule. So if you have, let's suppose, addition, you have a plus, let's suppose, b, and you have to form, suppose, this. So you'll take gradient of this and derivative of this and this. Same rules. So whatever rules we have learned in the symbolic, all these rules will apply over here. Okay, so let's now go to the forward trace. So we'll write forward automatic differentiation trace. Okay, starting with initially. So what we have to do is, if we want to find, so we'll find something like this. So we want to find, so if we have some vi, so let's suppose we have vi, so in this case we have v1, v2, we have these nodes. If we want to find the derivative, let's call that with this dot. So vi dot basically will be defined like this. This is derivative of vi with respect to x1, suppose. So in this case I just want to write x1. Okay, so this is what we'll define it as. Remember this definition. So if you take a derivative of any node with respect to input x1, so this is how we'll derive it. So this is actually, these are called as dual numbers. So each vi, so they have this called primal and they have dual numbers. So here I don't want to get into that terminology, I just want you to remember this. So you have vi, and when you take derivative of vi with respect to x1, so this is how we'll represent it. Okay, now starting with this graph, if you see this graph, so now this graph I can copy and paste everywhere wherever I want it. So this is my graph. So I'll copy it from here and I'll paste it over here. Okay, so if I paste it over here and I have to do forward automatic differentiation trace. So the first thing I'll do v1 dash. So basically I'll do v1 dot. So basically I want to find this. I want to find derivative of v1 with respect to x1. So I'm starting with this node, with this particular node that you see over here. So how to do that? Pretty easy. If you want to with respect to because it is x1. Okay, v1 is equal to x1. So if you take partial derivative of v1 with respect to x1, so that's equal to partial derivative x1 with respect to x1. So this is equal to 1. Okay, I think it's pretty clear so far. And then let's see, we'll see v2 dot. So we want to find the derivative of v2 with respect to x1. So how to do that? Now if you see this, if you see v2, it's equal to x2. If you take derivative of x2 with respect to x1, that is equal to 0. Okay, if you take partial derivative of this. Okay, I'll write arrows over here so to keep a trace of this. So we have then v3 dot. So how to compute this? So this is derivative of v3 with respect to x1. So derivative of this with respect to x1. So how to compute this? So if you see this, so how did we get to v3? So v3 was equal to, so we have to compute derivative of v3 with respect to x1. So we can use definition of v3. So derivative of v3 was log of x1. Okay, divided by, or not divided by, so by x1. So what you can do is, so after applying this, so you'll say, rather than writing the whole definition, I can say this was equal to v1, derivative of v1, because I have v1 with me. So once I take derivative of v1 with respect to x1, so that's already what I have over here. So I can say this is equal to, say, 1. I can write in the log v1 and then derivative of this v1. So derivative of v1 is v dash. Okay, I hope you got this point. So because v1, it is equal to log of x1 and x1 is equal to v1. So I can write that differentiation of that is equal to 1 divided by v1 and then multiplied by derivative of this v1. Derivative of v1, I can write it like this, v1 dot. Similarly, if I want to find v4, yes, we have a question over here. Yes, please. So here there is a minor mistake. It is log of v1, not just v1. So it's not just v1, So it was log of v1. So that's how we got. So we applied log on this. So this was equal to 1 divided by v1, and then by chain rule, so this should be derivative of whole of this expression again, v1 divided by x1. So this can be written as v1 dot, and I wrote it like this. Okay, now seeing v4. So how this v4 is, so if you see v4, how did you arrive at v4? So v4 was v1 multiplied by v2. So you can use product rule there. So if I directly write that, so that will be equal to, you can do the computation easily now. So v4 dot this will be equal to v1 v2 plus v2 v1, and then I'll use it like this, and I'll keep on substituting the values also here. So if you substitute these values, so this will be equal to 1 divided by 2, that is 0.5. Okay, and this thing over here, if you substitute the values, this is equal to 1.1 multiplied by 5 plus 0 multiplied by 2, this is equal to 5. Okay, v4 is equal to 5, and then v5 similarly, if you have to compute v5 dot, so what we will do is, so with this v5 you will say v2 dot cos of v2. Again, use the same thing. So how did we came up with v5? So v5 was sine of v2. Okay, so sine of v2 is this. So you take derivative of sine, that is cos of v2, and then you multiply it with derivative of v2 with respect to x1. So you're left with this, and you substitute the values. So after substituting the values, the answer is equal to 0 multiplied by cos of whatever, this is equal to 0. Similarly for v6 and for v7. Okay, so I'll write the values directly, and I know you people can now use these three rules: product rule, sum rule, and the chain rule in order to find that. So this v6 is equal to v3 plus v4. So this is equal to 0.5 plus 5. This is 5.5. Okay, similarly for this v7, so this was just subtraction. Okay, and you can use subtraction. So this is equal to 5.5 minus of 0. So this is again equal to 5.5. Okay, so now if I have to compute with respect to x1, so this is actually equal to derivative of v7. So this will be equal to 5.5. If I have to take derivative of y, basically the last y, because y, how did we get that? So y actually is equal to v7. So we take derivative of this, so v7 by vn, that's equal to 5.5. Okay, so this is how we took the trace of this. Okay, so we can repeat it again for if we have to compute this for, let's say, x2, we can repeat the same procedure. So repeat. So whatever the graph you saw over here, so you can take this as y. Okay, and you can compute the same thing with this. So let's say if you see, if you can again do the same thing for, we did it for x1 and x2. You can now take say v3 v4, and you can compute with respect to y. Okay, so now if you see, for each of this value, for each of x1, for each of x2, you have to perform the whole pass once. Okay, you have to do this. So what I'm trying to tell you, if you have a function f which goes from r of n to r of k, so this is the function, so it will need n passes then. So it will require you n passes. So because you have these n inputs, and it will require you n passes to do that. So each one of this, so usually in our machine learning, so this n will be greater than k. Okay, because whatever inputs we have, we will have a large number of inputs, and if you know that we will have these thousands of these, and this k is relatively small. So usually for this k, it will be a multi-class classification, say 10 classes. Sometimes maybe binary classification, sometimes a single number. So this n is way greater than k. So in that, the problem will be, so we'll have to perform a lot of these passes as we did this. Let's suppose for this x1, we'll perform one pass. For x2, we'll perform again n the pass. So we'll have to do it n number of times, and n is a huge number. So that's the problem with this, the forward case. Okay, and there is one more case now, because we saw that there is a limitation of this case as well. So the same procedure will be used, but we'll use this in the reverse. So that is called as a reverse mode of automatic differentiation. So we'll do this thing in the reverse now. So we'll do a reverse mode of automatic differentiation. Reverse mode automatic differentiation. So okay, in this, whatever the limitations we had with the forward pass, because we have to do n passes if we have the input length to be n, and that will reduce over here. So how to do that? In this, we'll define a term what's called adjoint. So this adjoint of v1, so we'll define it like this, v1 bar. So this will be equal to derivative of y with respect to vi. This is how we'll define it. So this will be called an adjoint. Okay, I hope this is clear. Again, the same, so local rule will be same. So if you have, let's suppose if you have a and you have b, you can use the same rules, a plus b, a multiplied by b. Okay, all these things will be same. Let's now take the reverse trace. Okay, we'll see a reverse automatic differentiation trace. I want to compute all of this. I want to compute v1 dash, v2 dash, because I want to compute this derivative of y with respect to y. That's what we want to do in the neural network. So you have a whole network, you have a computation graph of this sort that I am making over here, and you want to take the derivative of this with respect to all of these intermediate nodes. Okay, that's why I'm resorting to the backward path. I'm resorting to this automatic differentiation, but in the reverse mode. So how to do that now? So you have v7 bar first. So v7 is actually equal to y. So this is equal to dy, or I can say curl y by curl v7, or dou y by dou 7, partial derivative of y with respect to 7, because y is equal to v7. So this is obviously equal to 1. Okay, and now going to v6. Now v6, again, if you see how did we arrive at v6, so this is the v6. So this over here is v6. Okay, now we'll not go see initially what we're doing is we're saying v6 by x1, and then we're seeing how did we came over here. So we'll see, okay, we'll go in the backward way now. Okay, and we'll use a chain rule again. So this is equal to, so this v6 is equal to v7 bar multiplied by 1. Okay, so if you see why is it so, because v7 we took it from here, so v6 bar I should write it. Okay, I should not mess up the values also. So a v7 bar multiplied by 1. Why? Because I'll start it like this, because d of v6 of y with respect to v6. Okay, how can I write it? I can write it because it goes to that, because we have done enough of chain rule. So I'll say dv of v7 multiplied by v7 with respect to v6. Okay, this is how I can write it by chain rule. That's what I did here. So if you see, I said v7, so this is equal to v7, so this portion over here is equal to this, and this is equal to 1, sorry, so this is equal to 1. So this over here, the first term that you see over here, so this is equal to 1, and the second term that you see over here, so this is directly written like this, because this is by definition. Okay, so when I wrote v6 bar is equal to v7 bar by 1, so this is by the definition of chain rule. Again, if I do it for v5, so v5, again we can use the same chain rule, we can expand it, so you'll get this. So v5 is equal to v7 bar multiplied by minus 1. So again showing you this one more times. So if you have partial derivative of y with respect to v5, so this will be equal to partial derivative of y with respect to, because you have to see the coordinate graph again, so this is the v5, this is with respect to v7 again. So partial derivative of this with respect to v7, so this is equal to v7 multiplied by partial derivative of v7 by partial derivative of v5. Okay, so how did you get this minus 1 over here? Because you know that this is the minus times, this is not just y7, this is minus times of y7. Okay, so over here which I wrote is this is minus times of v7. That's why you got this minus 1 over here. So if you take derivative of this, so you will get, let's suppose, 1. Okay, so in this case I think dy, and if you see this, so you'll take the derivative of this, it will be minus 1 because of this minus sign, and you have this dy, and by definition I think this over here should be I can take this minus over here because it's in the multiplication. So from this I can say minus 1 is from this, and the v7 bar is from this. That's how I wrote this. Now coming back to v4, so v4 bar is equal to v6 multiplied by 1. You can again see the same things will keep on doing same things because it came from the plus. So here if you see, so this is a plus operator here, I think this v4, so v4 it came from plus operator, so this is the plus operator that you see. So how did we, if you want to expand it, so how can you expand it? So you have a v4 that's equal to this, so let me write it. So this is taking derivative of y with respect to v4. I want your attention here, and then this is v4 by, so again if you see over here, how did we arrive at this result? So this over here, so this was addition, so we'll take this, basically we got a derivative of this, and it was as a result of this, so we got this v6. So if you take v6, and v6 was v4 plus v3. Okay, if I write this v6, so this is v4 plus v3, this is equal to v6. So when you take derivative of this, let's say when you take derivative of v6, so one of these terms will vanish, so only one term will left, only one term will be there. So that's what I'm trying to, I think we have done this exercise previously also, so I think you people can easily, if you sort of expand these chain rule, and you will get these results. So you will have this v6 bar and 1. Similarly for the nodes where we have multiple of these things, so for this nodes, let's suppose if there is a node which is involved in the multiple one, you'll have summation for those terms. Let's suppose if I take, I think v3, v4, v3 can be done in the similar fashion. You will have to expand this. I don't want to go through the same exercise because we have done that in one of the previous lectures. And if you now take v2, or maybe yes v2, so v2 bar, so I'll just give the answer and you can figure it out because we have discussed these things at length also. So if you have a node like this, and if it is dependent on some other nodes of this sort, okay, and then you have something of this sort, and if you want to compute the gradient of this, so you add all of these things together. We have seen this also. So in this v2 node, if you see, so this v2 in the computation graph v2, so if you see the gradient goes from here, it goes also to here. Similarly for this v1, it goes to here and it goes to this. So there are multiple nodes involved, so you'll have to compute all of these things and then add these things together. Okay, we have seen this in the previous one of the sessions. So if I now write v2 bar, so I can directly write it as v5 bar multiply cos of v2. So I want you to pause the video at this point when you are watching the recording and try to derive this. I would have derived it, but it will take me more time here. So why? Because I'll first do it with respect to one node and then with the second node. Similarly for this v1 bar, so for v1 bar, I'll again have v4 bar multiplied by v2 plus v3 bar multiplied by 1 by v1, something of this sort, and then you can substitute the values that we have. Okay, I just wanted to show you like how it's done in this. So again, coming to this graph, so what did we do is, so we had this y, okay, and this y was over here v7. So we said we defined a term adjoint, so we said dy with respect to some vi, so curl of y by vi, so this was called as adjoint. So but I wanted you to just revise this procedure again. So we have seen this procedure in multiple times in previous lectures, okay, and now we'll do the same thing with our graph computation graph that we have. Okay, so this is the autograd method that we have also discussed in detail when we were deriving the backpropagation. I just wanted you to see how it's applied, and I want you people, when you are watching these videos, to pause it at least at maybe some places. How did we compute v5, how did we compute v4, v3, v2 and v1, and just make these calculations in order to see if you have understood these correctly. Okay, now we'll do the same thing with the code. Okay, give me some time, I'll bring you the code screen and then we'll do it in the code. Let's suppose now what we can do is we will define, let's suppose, these parameters, the parameters that we defined. Okay, if you have any questions you can ask me, because now I'll be doing the same procedure in code. That's why I didn't explain much the things over here, because I know I have to repeat these things, so I'll repeatedly use these things. I'll do these backpropagation. I'll have to update these gradients, so these gradients will be updated now manually. Okay, I'll not use any backpropagation, so whatever I have shown you on the screen, so I'll do the same steps but now in the code, and I'll explain you wherever the explanations are needed. Okay, just give me a second, I'll start from here. So now if you see, should I name these things also? Because I have no names of these. Okay, let me write the names also. Okay, for this, so this is the intermediate node, call that d. So we have d dot label is equal to d, and assuming that you have understood the previous code, the code that we wrote in the previous lecture. So now we have this f dot label, so this is equal to f. Please concentrate over here. If you are not concentrating so far, it's all right, but now because I am writing the code, we'll do the same exercise again. G dot label, this is equal to g. Now if I run this, okay, if I show you, now all these labels will be here. Okay, this is my expression. If you see the expression, so this expression is over here, so I can write the expression over here also. So this is the expression, g is equal to a multiplied by b. Okay, I'm multiplying this and then I'm doing addition of c. Okay, and then I am doing this multiplication with e. This is the expression that I have. So before this, I have shown you some expression and I show you the manually how do we do it. I showed you some complex expression like log of x1 plus x1 multiply x2 minus some sign of x2 or something like that, and we put them together. Now I have expression like this, a multiplied by b plus c multiplied by e, and now this is the graph of that, and I'll have to do the backward pass. Basically I'll have to update these gradients. So grad right now is 0 for everything, and I'll have to update gradients for this. Okay, starting with this g. So what is the gradient of g? So basically the loss function. So this is, if I have to compute d g by so this is with respect to g itself, because this is y. If I have to compute dy by dg, and because you know that y is equal to g, so this is equal to 1. I think everybody will agree with me on this point. Okay, dy by dg is equal to 1. So what I can do is I can write g dot grad is equal to 1. Okay, so if I just write this one, Okay, and I can also verify the gradient, because I have told you we can use numerical method of numerical method in order to verify the gradient. So we have a numerical method. So where is that? So if you see, this is our numerical gradient. Okay, so what we can do is we can just give it some function and then it will take the derivative of that. Okay, let's make some area where I can say, I'll say check. Okay, I will show you this. So this is gradient check. I have this function over here. I'll just comment it. So this is my gradient check. Okay, and I will give a function over here. So this is my function. Let's suppose if I have a function, quadratic function, which I have defined previously. So I just want to see if it is working. Yes, it is working over here. So similarly, now for this is your g. So you have this expression. Let's write the expression now. Instead of this quadratic function, I'll write the expression that we have. So we'll write the expression. Maybe we'll write it in this cell itself. Okay, say this is my function. We'll write it as function, and then we'll name it as, let's suppose, func, some function. Okay, if you see in the quadratic what was taking, so right now it was taking axis value. Now here you will have 4 values. It will take 4 values, a, b, c, and d. So if you see the quadratic function that we wrote, so this was the function. I think it was somewhere around this. So we had linear combination. This was our linear combination function. Let's take this, and we said return, and it was getting rid of a, b, and c. We'll give the same inputs, and we can go over here now, use the same format. So now it is having 4 inputs. So the inputs that you see is a, b, c, and e. Okay, actually I have written it as d, but anyway, a, b, c, e. By sheer luck, it was written like this. And now what will return? So we'll return and this expression. So this is the expression that I'll return, g basically. So we'll return this. Good that I have written it over here. If you have any confusions, do ask me. Okay, right now I'm constructing this. This is my function. So now this is my numerical gradient checking. So what I'll give is, I'll give the function, I'll give the corresponding, I think this is for the derivative. Now I should use this for univariate case. I should use the multivariate case, basically the partial derivative. I should not use this one. I should use the other function that we wrote. I think this is that function. Great. Now what can I do is I can copy paste this, because these things were explained in the previous session. So I will take this case over here, gradient check. Okay, and now what I can do is I can say function, and if I give some particular value, this is a, b, c, and e. Okay, this is my function, and I'll give this as input, and then variable index. This is the index at which the partial derivative with respect to what? With respect to this. Okay, and I'll give these inputs also. Okay, as in this case, if you again see the same thing. Okay, I want you to have a look at this. Okay, so in this case we were giving a naught, b naught, c naught. So in our case we'll give a naught, b naught, c naught, and e naught. Okay, and then we'll give this h value, the smaller value. Let's take the whole of this and we'll paste it there. To use the same code, reuse the code that we did. Instead of this, we should have this. Okay, now we'll use this func function. So this func function will be used instead of this linear combination. Okay, and now we'll have to define the values. Okay, let me define the values for you. I think we have these values are defined for us. So these values are defined, I suppose. This a, b, and c, and this is 2, -3, 10, 1.5. Can somebody just tell me the values? So what I can say, this is a naught, b naught, c naught, comma, e naught. So I'll write these values. So this will be a naught, comma, b naught, comma, c naught, comma, e naught. Okay, and this values if I take, so this was 2.0, comma, -3.0, comma, 10.0, comma, 1.5. Okay, so these are the values. Now if I need to take partial derivative, let's suppose partial derivative of the function. This is the function with respect to, let's suppose, some node with respect to e. In this case, this is e. Basically this is the value over here. So if you have this, so this g was we got this g by multiplying this f and e. Okay, we multiplied, this is the value of f, and this is the multiplier of e, and whole of this expression, if you see, so whole of this expression. So are we missing some brackets? I suppose we are. No, we're not. Okay, so this is, yes, good. This is good. So we have this function over here, if it is not visible clearly, so I'll just zoom it a bit. So this is the function that we defined. We said we have a multiplied by b plus c and multiplied by e. So this whole function is equal to g. So if I take derivative with respect to the whole function itself, so that's equal to 1. So there is no point of doing that, but you can still do that. Okay. So what you can do is you can nudge the value of whole of this function. You can perturb the value. Why do you want to perturb? You're perturbing the whole function itself. So that will be equal to 1. So this is pretty obvious. The first case is pretty obvious. So what I can do is, if I run this again now, so you will see gradient checking is not needed for first thing. So I think this is pretty clear. So we got gradient is 1.0. Okay, this was dy by dg. So with respect to this. Okay, now we'll start the important cases. So whatever we have seen in the writings, now we'll do it in the code. Now we'll have to compute dy with respect to this e. Okay, or we can call this dg or loss function. Okay, so let's call this, should we call this loss function? Anyway, okay, g is our loss function. So now we'll have to compute dg with respect to, say, de, with respect to e. So we'll have to compute this over here. So now if you see, how do we arrive at that? So we have two things to compute here. So dg by, once we have to compute this dg by de, so you see this is the this we got because we multiplied it. So we multiplied e multiplied by g. So we had this f, okay, and we had this f multiplied by e. That's how we got this g. So we are now taking derivative of g. Okay, let me write it somewhere. Take it over here. So what I'm trying to tell you over here is this. So if you have to take derivative of g with respect to e. So how did we get this g? So this is basically equivalent taking derivative of f multiplied by e, okay, with respect to e. Okay, and these are two things in case of multiplication. So you have this multiplication. When you have this multiplication, what you basically can do is, so this is your constant and this is the derivative, and you can directly say this is equal to f. This is equal to f. So whatever is the data of f over here, so that should be the gradient of this. Is everybody clear on this? Now if you see this, so we have to compute dg by de, so this is equal to f. So what I can do is I can just calculate the gradient. Again, coming back to the code window. So what I can do is, so this dg by de is directly equal to f dot data. So whatever the value of f is actually, so I showed you the derivation by this. Okay, if you see, so this is f dot data. So whatever is the data over here, I can assign this a gradient. So e dot grad is equal to f dot data. Okay, so if I take this and if I again run this one, so you will clearly see over here the gradient with respect to this got changed to e. Okay, let's do the manual check. We should check it now. Okay, we have to compute the gradient. This is the gradient function g, and this was, we have to take it with respect to e. With respect to e. So e has, what is the index of e? 0, 1, 2, and 3. So we can check it. So what we can do is, so this is the index at index 3. Okay, we'll take partial derivative of whatever this function is exact at, and we'll have to see at what particular place. So this is, okay, let me just see this numerical gradient I'm taking at position 3. This is a naught, this is b naught, and this is c naught. So I'm taking partial of a. I have to check partial of a. So if I run this, okay, I think this you can get it. I think exact, I should remove this exact value over here. This is not needed. Previously we were computing some exact gradient that I don't need. Now if you see this, the partial gradient derivative of this d or the loss function, so this is not d even, so in this case, in our case, this is g, this is equal to pi by a is equal to 3.99. so there is floating point problems. Okay, and now you can see that we wrote it again similar over here 4. So that's why I'm doing gradient check. I'm doing autograd and then doing the gradient check over here. Okay, so that's what I wrote, this function is gradient check. So we have this function over here, so I'm doing the checking. So I think this is clear for this. And now similarly for this, if you have to compute, if you have to do the same thing for this, so I'll just remove this. So if you have to compute now gradient of this g or the loss with respect to f, so how to do? Now again, you know, we have to take this data. So you have to take this data and fill this gradient over here. Okay, and we can check it also. Okay, now what we can do is, so again the same thing. So let's call this f dot grad. F dot grad is equal to e dot data. If I run this, so whatever it was, so if I run this again, so this over here, if you see, f the gradient is 1.5. Okay, now let's start with this. So we have, this is our graph. So what we did so far is, so we performed with respect to this. So this was equal to 1, pretty easy case. And now that then we saw how how this multiply behaves. So how this multiply behaves, it distributes the gradient somehow. If you see, so how did it do? So you had this, you had, let's suppose this data, it went to this case. Okay, it went to this, and you have this data of this, it went to this. So whenever you see multiplication, okay, you see multiplication of two nodes being done. So you have a multiplied by b, and you have to take gradient. So what you have to do is you have to swap. That's what I wrote fan out. So if you see previously what I said is, so you have this Let's suppose take gradient and then you find it out. Again, I'll take the interesting node and then you will understand it more thoroughly. So now we'll take this. So we substitute the gradient. So we'll take this case now. So we'll take this C and D. Okay, starting with D. Okay, now let's start with D. So this is what we have to do. We have to compute derivative of G with respect to D. Okay, now we know how to do that because this is dependent on what? So this D actually is we got it from like somehow from F, and then we, so if you see the whole graph again, if I show you the whole graph, so keeping this D in the view, so this is the graph. So you have, I should write it above, so dg by d something of this D, let's write it D. So if you see this D, okay, this will get its things from this F. So this F in turn we got it from G. So we'll again use chain rule. Okay, now if you see this, so till here we have everything. So if I have to compute this, I'll write dg by df, or derivative of G with respect to this F. Okay, and multiplied by derivative of F with respect to dd for this D. If you see this particular D, so how do we get here? Because we are involving this F over here. So how did we get with this F? So this F was C plus D. If you write this, so this you already know. This particular you already know. You have computed this. So this you have already computed. I'll let it tick. Okay. And now this is local gradient. So I can call this local gradient. How? Because let's suppose consider this huge graph. Consider the huge neural network. So you have one node, and this node was having some other nodes in following. So what you can do is, so this is my local gradient. I only know that let's suppose I am D. So I'll be asking like, what did I do? I said, okay, I just did something which produced F. Okay, so if I nudge myself, I know what will happen to F. So if I am thinking as per the D node, so D node will think like this. D node will say, okay, so I am D. So what I did is this plus operation was made with the C. I produced F. So my contribution is only in producing F, and I can give the gradient with respect to F, and I don't know anything else. So that's why I'm calling it local gradient. So why is this local gradient? Because so this D is only responsible for F, and then F knows the whole story. F says, okay, I'll take care of the rest of the story. The rest of the story is this: you have to compute dg by df that we already computed. Okay, so in this particular case, so you can compute this. Okay, if you compute this, you already know this. Okay, so that's why initially, if you see me writing these formulas, which I didn't write like fully, so basically that's the story. The story was this: if you have in addition, so you have these addition now. So what can you do is, so you'll say, I can compute my local gradient. So this I'll assume you know. So this I'll assume. So this part I'll assume you know because you have computed. It came from some other node which I am not directly involved in. I'm indirectly involved in, and now I can compute this. So this part over here, I'll compute it here. So this df by dd. So this is equal to, how did we get this f? So this was equal to C plus D. So this is equal to C plus D. Dou by D. And now you know how to do this. So this C will be treated as constant, and then with respect to this D. So if you see this over here, so this will be treated as constant, and this will be treated as variable. So if you have to perform this, so treat this as constant, this will be 0, and with this will 1. This will be equal to 1. So if you see, this is equal to 1. Everybody agrees with me on this? So what will happen now? So in case of plus, so when you have this plus node over here, so what will happen? The gradient will directly transform. Whatever f you see over here, so whatever value, the data that you see will be transferred directly over here. Did you get me at this point? So what I'm trying to tell you, if you have plus node, okay, and you have to take a derivative d, and then you did some plus operation, and then you produced f node. So what I'm trying to tell you here is this, that D is saying, I don't know what f is involved into, but I can tell you if I nudge myself, so how will f be impacted, because I am producing just f. So okay, so I can give you the local gradient. So in computing gradient, if it is plus involved, so you will see that dou C plus D. So if I'm taking C plus D, because that's what f is equal to. So what I will do is I'll treat this as constant and this as variable, this D as variable. So that this will be equal to 1. So what I'm trying to tell you over here is, so you will directly get this value, and then you will directly transfer it over here. And the similar thing will happen for the C case. So how many of you people agree with me on this point? So if you see this, what is the local gradient? So we computed local gradient over. So local gradient is equal to 1. So it will, whatever gradient was there in the node which was in front of it, it will just pass it on. It will say, okay, I am a plus node, I don't care. So whatever is the gradient was before me, so I'll just transfer that. Okay, we'll do that. Let me just erase these diagrams now in order to, I'll make it a little cleaner. So now here if you see, so I was computing So I was computing this. So I was computing for this node, particular node, dg by dd. So this is what I was computing. So I said, okay, what is this equal to? So this is equal to dg by df, because it knows about f, and multiplied by df by dd. Okay, so this I called it as local gradient, and this was global gradient. So this over here I can call it global gradient. So this I know. Okay, so this is equal to this I know already. So dg by df, if you see dg by df, so basically a gradient of this. So that is, so if you see f dot grad, so this is equal to f dot grad. So I can write it f dot grad and multiplied by, so what I did is, then I said this multiplied by 1. Why multiply 1? Because the local gradient when I computed, so it is equal to 1. So what effectively this plus node is doing, whatever gradient was in front of it, it is just transferring it. It's saying, okay, if I'm a plus node, whatever gradient is in front of me, I'll just transfer it. So what I can write over here is then, so I can say d dot grad, because I'm doing the gradient of this, is equal to whatever is the f dot grad. Okay, so if you run this, so if you again run this, so I'll run this dot, so you can see this d dot grad got the gradient, whatever is the f dot grad. Okay, f dot grad was 1.5. Okay, now if I have to check it again, see how to perform the checking. So now this node over here, so if you see, so for this node, I think this checking is for this node again. The same thing will be over here. So because we have this 1.5, so same whole procedure, the same procedure over here is what applies to this, which we did again. So here I am doing this. So I am making nudges. So I have this whole g function. So this is my whole g function. Okay, and if I want to nudge some value, I'm saying, okay, nudge with the particular value of this. So with respect to this, let's suppose d. So how did we get d? So d was, we got it from f. So we can check it with this gradient. I think this gradient checking is now pretty obvious if you see it. So I think this is the case. And now for the other case, let's suppose we have this d g by tg by d, and then the other thing was c. Okay, this again will be equal to dg by, so we will start with what? We'll start with f again, df multiplied by, okay, this is the global gradient, and multiplied by local. So what is the local? So df by dc, because c will tell me, okay, I know what I did with f. So if I nudge myself, I'll tell you what will happen to f. So I can tell you the local thing. Okay, and then you will have to ask f. Okay, and we have computed that, we have pre-computed that. So now you know that this thing over here, if you again calculate this, the local gradient is 1. So this will be equal to g dot grad, not g dot grad. So this will be equal to f dot grad again. So if you see this, so this f gradient, so plus node actually just transfers the gradient. This will be f dot grad. Okay, if I just put this c dot grad is equal to f dot grad. I run this again. If I draw this, you can clearly see over here. Now the c got gradient, d got f and e and g, and now we're at most interesting node a and b. Okay, not most interesting because we have, if you understood this c and d, you understood everything. You understood the whole back propagation. That's what you do. You just take the derivative of what came before it, like in the backward pass, and then you multiply the local gradient. Okay, now again for this we'll take it for a also, a and b. So now what we have to compute is this. So you'll have derivative of this g with respect to a, okay, and derivative of g with respect to b. These are the two things that we compute. But you see over here, so multiplication is involved. So if I ask b, okay, if I nudge you, how is g impacted? It'll say, oh, I don't know, I have nothing to do with g. So what? Okay, then how have you impacted the graph? It'll say, okay. So if you ask me, if I ask this a, so what have you done with g? I don't know, I have done something to d. If I nudge myself, I know how d will get impacted. Okay, tell me that. So I'll tell you this. I'll tell you the local gradient. So g by, I know with respect to this particular d, and then multiplied by partial derivative of d with respect to this a. So this part a knows. If I ask a this question, a says I know this part. Okay, this is the part I know, but this is the part I don't know. You ask this to g, and you know we have calculated this. So we just calculated. If you see dg by dd and dg by dc, we calculated right here. So these two things are calculated. dg by dc and dg by dd by calculated, whatever is in the previous node. So what we can do over here is, if you see this, you have to only compute the local gradient. So how to compute locally in terms of multiplication? Now if you have multiplication, Okay, so now this is checked, we know this already. Okay, so I'll just keep check on this. So now we have to compute gradient of this with respect to a. So how did we form this? So how did we form this d? So it will say I did a multiplied by b. Okay, I did a multiplied by b, and then you have to take derivative of this with respect to a. And now this a is a variable and b is constant. So what is the, if you directly use this, this will be equal to b. So if you know this, now you have this value equal to b. This is the value of b, not the gradient of b. So you see, this is the value over here. So you take this b. Okay, you have this value of b. So because you are taking a multiplied b, so you take when you apply partial derivative on a multiplied by b with respect to a, so you will get just b. So if in order to compute this, so this whole expression will be a, and you should take the value from this. So consider this to be out. So this is the whatever was the output, and this is the local gradient. So you have a multiplied by whatever gradient was passed to it. Okay, now let's do this again in the code. Okay, I'll hide this. So I have to compute now. I have to compute dg with respect to a, and dg first will do this. So this is dg with respect to a. So I am telling you, so this is dg by d. So whatever it impacted, dg by dd. Okay, and multiplied by the local gradient. So local gradient is dd by dA, and this is my local gradient. So on seeing this, you know that this is equal to b. So this was equal to b dot data actually. Okay, so this was equal to b. So this portion, if you see over here, if you have to expand it, so d was equal to a multiplied by, so this was a multiplied by b. Okay, and then we can take the value of this and directly see this. So we have this over here. So this will be dg, we already know it. So this dg by dd, this dg by dd is d dot grad. So we'll take this d dot grad because we already computed, multiplied by. So what to multiply it with? So we'll multiply it with this particular d by da. So this d by dA, or this is a partial derivative of d with respect to a. So how did we get that? So that's equal to b. So that is equal to b. So we'll take b dot value, or b dot data, I think. So b dot data in this case. So if I have to take this, so I'll say b dot grad, or a dot grad is equal to this. Okay, so this is b dot data. And now if I set this, if I again run this, so you are seeing over here, so I am putting a gradient is minus 4.5. Okay, I hope you are getting this. And similarly, now if I do it for this b, so similar thing will happen. So I'll say this whole expression with respect to b. Okay, with respect to b, so this is equal to dg by dd multiplied by this by db. Okay, and this, now if you expand, you will be remaining with a dot data. Okay, because you have to take a dot data, because this will remain, and this will be taken to 1. So if you now take this d dot grad and a dot data, so this will be equal to b dot grad. Okay, so now effectively what is happening? If you have plus, it is just transferring whatever gradient was there in the node that is in the computation graph after it, so it will just take the gradient. But if it's a multiplication node, what it does is it will take the gradient whatever it was, it will multiply it with, let's suppose it was a multiplied b and it was a multiplied by b, suppose. Okay, so if you are computing gradient for this, so what you will do is you will take value of this node, okay, and you will multiply it with the gradient of the neuron or the node which came after it in the expression graph, okay, and in the computation graph. Similarly for this b, you will take the value of this a, you will take value of a, whatever the value was there, and you will multiply it with the gradient of the node that came after it. Okay, if I just multiply it with this, so you will now see, if I show you this draw dot d, so you are seeing that this is equal to 3.0. So what actually happened? So this was the data that we took. Is data similar? Yes. Okay, now we have computed all the gradients. So whatever nodes we had, we have computed gradient. So what effectively should happen is we want this g to be less, because let's suppose this g is a loss function, this g is a loss function at the end, and right now the value, if you see, is 6. So by the help of gradient descent, if I take all these gradients, so I have computed all the gradients, if I take these nodes and if I nudge these values a little bit, except g, let's leave the g aside, if I take f, e, c, d, a and b, so if I use gradient descent, if I take these values, whatever the gradient of these values are, so I'll just apply some learning rate. Okay, let's do that. So here, if you see this, I'll do that updation here. That is the thing that Jupyter gives me. So I'll do updations and I'll see if I can get less loss. Updations. So what I'm now trying to do is, because I have gradient for every node now, so I'll say starting from f. Okay, starting from f dot data. So whatever data it has, this is equal to, I can say f dot data, and then subtract some learning rate 0.01 multiplied by whatever is the f dot grad. Okay, I suppose you got this. So now this is applying the gradient descent on this. So we have e. Now we have this e. Okay, and we'll say e, and we'll say this e. Okay, and now we have c, d, a, and b. Okay, so what I should do is I should write minus equal to, anyway this is all right. So you have c. Okay, I'm writing it slow on purpose so that you get the time to grasp it. Now we have d. Till I just change this, understand the thing that I'm saying. So what I was telling you people is that you have the gradient now, you have the data also. Now you know that if I have the gradient, it is in the steepest ascent and you have to descend it, and I'm using that learning rate over here. So now this is d dot data, and now we again can use, this is f, c, d, e, and we have a and b. So we can use a, and let's say we can use b also. We should use b also because all these are the parameters of the model. Okay, so right now if you see the value, if I draw this dot, so I am drawing this, so you are seeing the value to be 6.0. okay, I'll have to also perform the forward pass. So why I'm performing the forward pass, so this is why the forward pass is happening. This is my forward pass. So if you see this value over here, so this is forward pass. This value over here is my forward pass. I'll take this out. Okay, I'll say this is what this, I'll say this is my forward pass. So when I'm running this, okay, and these are my updations, so I'm doing updations over here. I'll take all of these values, so I'll paste it over here. I'll take these values also, paste it over here. So this is basically my manual backpropagation. So what I'm first trying to do, I'm applying the forward pass. So this is my forward pass. See, so this over here is my forward pass. So this is my forward pass. Okay, then what I'm trying to do is I'm trying to apply the gradients. So okay, I'm trying to do manual backprop. So this is my manual backprop. So that is what I have written over here. This is my manual backprop, and then this is the updation, or this is my gradient descent. This is my gradient descent. Please carefully look at this. So I'm applying forward pass. Okay, so I'm applying forward pass over here. So I'm running this. I'm showing you this dot g. Okay, I should draw it after this. So I'll draw it after this. Because after forward pass, I'll draw this. So run the forward pass, draw this g. So gradient is still preserved. So I'll just, for the sake of completion, the gradient. So now you see these are my gradients, and I have performed the first thing is this was my forward pass, and then I showed you how this looks after forward pass, and then I am applying gradient, and I showed you the gradient, and then I'll update these things. Okay, because I want this g value to be less. Okay, let me apply the step of this. So I am applying gradient. Okay, so if this applied the gradient, so it actually update the data. So after this, I'll apply forward pass once more. So I'll apply forward pass, and now if I show you this, if I again draw this, so you can clearly see over here, if I see the data got changed, this g went to 5.5. Okay, initially it was 6, it now came to 5.5. Again do the manual backpropagation. Okay, again do the gradient descent. If I come back again forward pass, oops, if I do the forward pass, it was 5.5, remember that. So if you do it again, you are seeing loss goes to 5.08. Okay, let's do it one more step to show you, at least to feel satisfied that we are doing it right. So now we again do the manual backpropagation. Okay, we'll do the updations. So then run the forward pass and then run it again. So now if you see, this is going to be 4.6, and we want it to be 0, and it will take iterations. You will keep on, basically right now what we're trying to do is, again if you see this, so 4 steps involved. The first step was forward pass. The forward pass is the main step, that because we have to do the forward computation. So once we perform that, and then we drive the graph. So once we draw this graph, so what happened, it gave you the gradients, and if you see, the gradients are going to 0. So these gradients are going to 0, and now you see the gradient. So this is called vanishing gradient problem. So we'll handle it separately. And then we are doing the backward pass, forward pass, backward pass, updation, forward pass, backward pass, updation. We keep on doing this loop. This is called training. So if somebody tells you what is training, so in training you perform forward pass, okay, then you perform backward pass, okay. So after that, what you do is, so once you have that, so you again do the updations, and then you keep on rolling this forward pass, backward, update, forward, backward, update. You keep on doing this, and this again, if I show you this one more time to see if it is again reducing. So draw this. So this value is 4.6. Do the manual backpropagation, do the updation, do the forward pass, and draw this. So this was 4.6. This is 4.2. I think this is working. So how many of you understood whole other thing that I said so far? So whatever we did previously since like 9, 10, 11 lectures, so this was actually for this. Okay, so when you write the code, the most important thing will happen. You will get the clarity. So there is a famous quote: if you cannot produce it, or if you cannot make it, you don't understand it. So here, what I have shown you is how to train a neural network. So you do forward pass, then you do backward pass, and then you updation. Again, you do the same loop. You keep on doing this. So this is called training. So in this, if you understood this, so while watching these lectures, you pause and then you think about it. Okay, what is happening underneath? And in this lecture, I have given you one example on the sine cos. So you should do the same procedure what we did on this example: a multiplied by b plus c and whole multiplied by e, something of that sort. So you should do the same thing with that. That's a little bit tedious example, and I left some calculations there on purpose so that whenever you watch the lecture, so you'll just reason about it. You'll say v5, so how to compute that? How to compute that on paper? So once you do that on paper, and then you'll use this computational method of differentiation, which is called as reverse mode of automatic differentiation. I hope you understood some things of this. Also, in the next session, we'll take some more complicated example. So we'll take a neuron, and then we'll do for a single neuron, we'll try to train a single neuron, and then from that single neuron, we'll make a stack of neurons. That's a layer of neurons, and then we'll put these layers together, we'll connect them together, and then we'll form a network of neurons. But if you understood this part, you have understood heart of deep learning. There is nothing to learn more conceptually. You don't have to learn anything. And the problem that we're left with now is engineering problem. You have to perform this efficiently. You have to write the code so that people understand it. But if you have understood this far, I think you are done with deep learning. Like for most the time, people have this, like, how is backpropagation being done? How is this being done? How is that being done? You should not have these questions. And rest of the things are just for the efficiency purpose, and they're just engineering aspects of that.